All right, so let's go ahead and get started. Good morning, everyone. Just a couple of quick announcements. You have a hand-in homework number 3 that's posted on Moodle for you due this Thursday. Then you have a couple of other online homework assignments. So Chapter 3, Part 2 is due tomorrow, this Tuesday. And then Chapter 4 will be posted later today, and that will be due on Friday. So remember, you kind of want to think about having assignments due Tuesdays and Fridays. Sometimes we'll skip those days, but just so you're kind of on the radar for Tuesdays and Fridays for online homework. Just a quick reminder that, we've been told by the university to only correspond with students through university email addresses. So please do use your student email address when emailing instructors or professors. Then, another reminder that your first exam is coming up on October 6th, and that's a night exam. Plan ahead. Don't make any plans for that day or leaving early for the weekend or anything. I will say that because I'm asking you to come outside of class time, we will not have class on Friday, October 7th. So you can also put that on your radar. But do make sure that you're available for the Thursday night, October 6th. Okay? A couple of just brief homework comments, I guess. So when you're talking about your distribution, and this might seem like a very minor point, but we just want you to get in the habit of using correct grammar. When you're talking about a distribution, the distribution of a quantitative variable can be skewed to the right or skewed to the left, but we don't talk about the histogram itself being skewed. Okay, that kind of takes on a different term, like the histogram itself is skewed, but it's really the distribution. So you want to just talk about the distribution rather than the graphical display itself. Okay. If you decide in a report that you want to remove outliers so that it makes the rest of the graph easier to see, that's an acceptable thing to do. But we don't want to just get in the habit of just deleting outliers because they're inconvenient. Okay, we'll find a lot of scenarios where outliers actually tell us a lot about a situation often, or a lot about our data, and they can be very interesting. So unless we know for sure that that was some type of a recording error, we don't delete those observations. But to make a graph easier to construct, you might say, well, here's the box plot of these heights for our 400 students. However, there were 2 unusual points, and list them in your description. So just make sure that we don't just delete our data. And then another thing, just in terms of just watching how you're saying something, in terms of the bird species problem, don't write the distribution of bird species is, because remember that this was for that Christmas count data from your last homework assignment. It was the number of species per site, right? So per site where people were gathering to count these Christmas bird counts, to count the number of species. Okay, it's not the distribution of bird species. Okay, that's different, which I'm actually going to show you something really cool in just a minute. Okay, it's not the distribution of bird species, it's the distribution of the number of species per site. And so those are 2 completely different things just by that one word that you're leaving out, okay? So just be careful with that. And then just if you feel like you need some practice with those descriptions, have someone else read them for you, bring them in to us, we can read them for you and critique them, okay? All right, so moving right along with this bird species point, I just wanted to show you this really cool map. And the reason why I show this to you is because it's just another way to display some really interesting data very effectively. And so let me tell you, this is from a website called allaboutbirds.org. And it's kind of hard for me to get the whole picture on the screen here. But it's really a time map of different, so each of these is a different species of bird, each dot. And so it's showing you the migration over the whole year of those different birds. Okay, and so I just think it's a really beautiful map that shows you how these birds are moving throughout the season. Okay, so you can go to this website and they have a whole description of all these data that they've collected. So here we are, and then here they come back down. This is probably right about now. We're moving into September. So here's what's going on right now with all those different species. So going back down through Mexico into South America. So pretty cool stuff. Okay. And then here's also, you can click on this, and then it shows you these little numbers here when they start moving. It can show you, it's a different key, it shows you all the different types of birds that those are. So you could look at these numbers and actually figure out, oh, well, what's this bird number 87 up here in northern Canada? And you can go all the way down here. 87 was the Smith's longspur. So I don't know, it's just kind of cool. I wanted to share that with you on this Monday morning, getting you excited about different ways to display your data. And then also, I wanted to motivate this as well. Hopefully I can find this one last link that I wanted to show you. Okay, so they show you this paper that was published in January of 2016. Okay, and they have lots of interesting information that you can grab and look at. But, oh, and then I clicked on this and now it's going to start. Oh, here we go. So this is what I wanted to show you right here. Okay, so what are these called? Box plots, right? So they have a whole section of box plots that they've created. And I'm not going to spend a lot of time, but I just want to let you know that you can go here and look at this. But let's just look at this one graph and see what they're trying to do here. So they have done a really nice job here trying to really show us some differences and similarities between these. So on the y-axis, they're showing us the migration speed, okay? And then they have, you know, the season. So they have spring and autumn, spring and autumn, spring and autumn, spring and autumn, and so on. So the first thing that jumps out at me is that in the spring, they tend to have a higher migration speed than in the autumn, right? In every single color, there's a higher migration speed. So that might be, we're going to talk a lot about comparisons today. So that might be one of the first things that I kind of grab from that graph. Okay, and then they break this down by the different migration patterns that they might have. So clockwise, anti-clockwise, repeated oceanic, repeated terrestrial. So anyway, I just wanted to show you that, showing you this is, you know, top-notch research going on, and they're including these box plots that we are learning about more today. So that's all I have to say. Let's go ahead and jump to that learning catalytics question. And get started there. Okay. So I'm going to go ahead and, okay. So just tell me, select all of those displays that would be appropriate for visualizing the distribution of a quantitative variable. So this is a many choice question, so I want you to select as many as you see appropriate. And you can talk about it with your neighbor, you know, if you want to have a little conversation about it. and take maybe 10 more seconds, and then we'll talk about this question. All right, and if you haven't already submitted your question, even if you don't feel confident, go ahead and submit a question, because a large of this is participation-based, so go ahead and submit it, and then we'll talk about it. That's the whole idea of these questions, is just to get some thoughts flowing here. So let's go ahead and stop the delivery, and we'll look at those results, show all the results to you. Okay, so everyone, or most everyone, thinks a histogram is appropriate, so check. Box plot, check. Okay, C, bar chart and segmented bar chart. So bar chart is for a categorical variable. Segmented bar chart is for the relationship between two categorical variables. Okay, so C and D, we don't want to put those in. A lot of you decided not to choose those. Then we have a stem plot, quantitative, okay, dot plot, quantitative, and then pie chart, of course, is categorical as well. So it looks like a lot of you are on the right track there. If you missed any of those, then now this is a nice summary now that we have all of our graphical displays all together, okay? All right, moving right along to the next question that I have for you. Okay, so this one is going to pertain to what we learned at the end of class yesterday. Which of these numbers has the largest standard deviation? Okay, so I'll remind you that the standard deviation is a measure of spread, right? And I don't expect you to actually be calculating the standard deviation here. I just want you to, to think about it, talk about it with your neighbor. Just take about, 30 seconds or so, and then we'll talk about that one as well. Right, just about 5 more seconds. Again, no need to make a calculation. All right, so I'm going to go ahead and stop that one, and then we'll show the results here. All right, so it looks like most of you have the hang of that one as well, right? Just the measure of spread. So it's not an exact interpretation, but just thinking of it as the average deviation from the mean for all of those points in your data set. So clearly B, those are the ones that are most spread out. And the reason specifically why I wanted to put C in there is so that you would realize that it has nothing to do with the size of the actual data values, right? It's not a measure of how big they are, because these are the biggest values overall. They have the largest mean. But it's a measure of, on average, how much are those deviating from the mean. So just to keep that in mind. Is that okay with everyone? Okay. Okay, so now we have 2 of those main pairs. We have median and IQR. We have mean and standard deviation. So when do I use which, right? Why do we even have 2 pairs? Why don't we just have 1 pair to go with always? And so now that's where we're headed today, talking about resistance on page 38 is where we're going to start off. Okay, we've already explored this idea of resistance in lab, but we haven't actually defined the term. And so now this is just going to be a basic definition for you of resistance and sensitive measures. So A measure of center or spread is said to be resistant to outliers or skewness if it is not greatly affected by changes in the numerical values of a small proportion of the observations. Okay, and again, we have a lot of vague terms here, right? By a small number of observations, well, how many is small? Okay, it really just means that we're not going to be, that measure is not going to be greatly affected by, you know, those large or very small values relative to the rest of the distribution. Okay, so a measure which is not resistant is said to be sensitive. So resistant, sensitive. Let's go ahead and just give a quick example. Okay, let's think of our Ginkgo data. Okay, that we had on Friday that we were working with finding the 5-number summary for. Okay, and let's say that this 14 accidentally, that last 14 got accidentally recorded as a 144 instead of the 14. Okay, so what is that going to do to the median? Okay, so if the median, what do you think is going to happen if I accidentally do that 144? It's going to stay the same, right? So stays the same. Okay, and the median of these data was 3 points. Okay, what about the mean? What do you think is going to happen to the mean? Yeah, exactly. It's going to, you can think of it, visualize it as pulling the mean toward that 144. Because remember, we add all these data values together and then divide by the number of points. So this 144 is going to, you know, contribute a lot more to that sum than the rest of the data values, and therefore pull it up. So the new mean is going to increase from, it was 3.5 points, and it's going to go up to 4.72 points. Okay, so it gives us quite a lot different result just with that one additional, with that one error that we made. Okay. Okay, so putting all of this together, the median is therefore, just based on this, you know, one example, we would say that the median is resistant to outliers, and the mean is what? Sensitive, right? Meaning that the mean might not be the best choice if we know we have a few outliers in our distribution, because it's not going to give us a nice perspective on what the center of the distribution looks like. Okay? Similarly, what do you think about the range? Remember, the range is a single value, max minus min. Do you think it's going to be resistant or sensitive? Yeah, right? It's going to be largely sensitive. Okay, this is why we really try not to use that as a main measure of spread. Okay, because it can really be affected because it's, you know, just by definition, right? The maximum minus the minimum. It's the most sensitive measure of spread that we have. What about the IQR, the interquartile range? So this one is actually going to be resistant because it's based on those, right? It's the range of the middle 50% of the distribution. So it's not going to be affected by outliers on either tail of the distribution. So that's going to be resistant. Okay, the standard deviation, what do you think about that one? Let me remind you of what that looks like, right? This fun little formula here, divided by n minus 1, take the square root. Every time I get a standard deviation, I take into account every single data value, and I use the mean, which we have said is sensitive. So what do you think is going to be true about the standard deviation? It's going to be sensitive as well, right? It also takes into account every single data value. and it's based on the mean. So it is also going to be sensitive. Okay? So I kind of explained to you why this is the case throughout each one, so I'm not going to write that down. But basically, the median and IQR are based on position within the distribution, where the mean and the standard deviation take into account every single data value. And so when we have a really large contribution to the sum in the mean or the standard deviation, then that can really largely affect those measures. Okay? So basically, when we have a distribution that is skewed or has a lot of outliers, we're going to try and use the median and the IQR rather than the mean and the standard deviation. Okay, and I'm going to say more about that on the next page, right after we talk about what we can expect when we're looking at different types of distributions. Okay, if I have different shapes of distributions, how can I expect the mean and the median to be placed in relation to one another? So let's look at these three common distribution types: symmetric, skewed right, and skewed left. These are the three main shapes that we're going to be experiencing. Okay? If I have a symmetric distribution, then I would expect the mean and the median to be, if it's perfectly symmetric and unimodal, then the mean and the median would be exactly the same, right? Okay, so let's just go ahead and draw that in for ourselves. So we have this symbol, y bar, for the mean, and the median is big M, right? And so those are just going to be exactly right on top of each other if this is a perfectly symmetric distribution. Okay? If I have a skewed right distribution, remember that the median is still in the exact middle of the distribution. Okay, so this is sometimes hard for me to eyeball, but the bulk of the data are in this, this peak right here, so maybe even a little bit left would be the median. Okay? So then all of these values, remember that, think about this on a number line from smallest to greatest. There are some big values up here that are going to pull the mean to the right. So then the mean is going to be to the right of the median. Okay, so if we have a skewed right distribution, the mean is going to be greater than the median. This does not mean, however, that you can tell a distribution is skewed by just looking at the mean and the median, right? Because you could just have one giant outlier and the mean could be a lot greater than the median, and that does not mean that it's skewed. Okay, this is a one-directional argument saying if we have a skewed right distribution, the mean would most likely be greater than the median. Okay? Similarly, a skewed left distribution, again, the median is still in the exact middle of that distribution, and the mean would be to the left, right? Because then those smaller values are going to be pulling the mean to the left. All right. So finally, to summarize everything that we've kind of outlined for you here in the last few pages, we want to know, well, when should we use which measures? In what situations should I use the median and the IQR? In what situations should I use the mean and the standard deviation? Okay? Let's just look at this table. So let's say that I have a symmetric distribution with no outliers. Okay? Something that looks like, the heights of all Stat 216 students. Nice and symmetric, not perfect, right? But reasonably symmetric, no outliers, okay? So the mean and the standard deviation are definitely appropriate in this scenario, right? So that's a fine measure of center and spread. However, the median and the IQR would be justified as well. There's nothing wrong with using those, okay? It just turns out that the mean and the standard deviation are, one, more commonly used in, in literature, and then two, the methods that we are able to learn later on, these inference procedures that we're going to learn later on in the course, they're based on the mean and standard deviation, and they end up having a lot of nice properties that allow us to carry out some nice procedures. So if we can use the mean and standard deviation, we tend to use that, but there's nothing wrong with median and IQR. They're awesome measures too, okay? If we have a skewed distribution, then the median and the IQR are going to be the best measures of center and spread that I have, okay? Another way that you could do this, let's say I have a symmetric distribution, looks pretty good, but then I have a few really unusual points or outliers. So what you could do is, one, median and IQR, or two, you could give the mean and the standard deviation both with and without the outliers, just so that you can educate your reader about how much that mean is actually being inflated or deflated by those outliers, okay? But again, we don't delete outliers, but it is acceptable to report summary statistics with and without the outliers, okay? Good for everyone? Okay. All right. So now I just want to do two final summaries for you, and then we're going to do a couple more learning catalytics questions, and time permitting, then start getting into chapter 4. Okay, so we have already looked at both of these distributions, but this was before we had our numerical measures of center and spread to incorporate into those descriptions. So now I just want to go back and give you two final descriptions of those distributions for you to have in your notes and for you to work from when you're making those, when you're creating those descriptions. So first of all, let's go to those eruption interval data. You don't have to look at them. I'm going to put them up here, those eruption intervals. And we already incorporated one description where I went through these important features. I'm just going to leave those up there since we still need them. But now, instead of just mentioning a general center, I'm actually going to incorporate either the mean or the median. And, I'm just going to go ahead and use the median since I have a few values down here that might be, pulling the mean down a little bit. But I think that the mean would be mean and standard deviation would be okay in this problem. All right, so let's go ahead and start our description. Okay, and again, just keeping these guys in mind here. Okay, it's always nice to just talk about exactly what you're describing in the opening sentence. So the distribution of eruption intervals for Old Faithful Geyser okay, and please give me as much information as possible, right? If you just say eruption intervals, that's some context, but you need to tell me, well, it makes a lot more sense to tell me this is from Old Faithful, guys, come on, and it's from 2011 to 2012. So just giving me everything I need to know about where the data are coming from. So distribution of eruption intervals for Old Faithful Geyser, okay, is fairly symmetric, or you could say slightly skewed to the left. Either one is fine. Okay, so we'll just say fairly symmetric and unimodal. Okay, and you would grab this off of StatCrunch. It's not like I'm just saying, oh, the median is clearly 89 minutes there. Okay, I grabbed this off of StatCrunch with a median of 89 minutes. And an IQR of 8 minutes. Okay, so just in that, with just one sentence, I have given you context. So I'm going to do a double check here. So I've given you context, I've given you shape, I've given you a measure of center and a measure of spread. Okay, so I've told you with a median of 89 minutes and an IQR of 8 minutes. So just by giving you that first paragraph, you should be able to kind of visualize, if you could close your eyes without actually being able to see that distribution, you should be able to somewhat visualize what that looks like. Okay? Then the next sentence, if I want to, I could add in this little, these little unusual eruption intervals that are a little bit lower in the left tail there. So we could say, something like this, approximately, and this is again, from me looking at the distribution, getting some more information from StatCrunch. So I'll say approximately 1% of the eruption intervals were between 37 and 60 minutes long. Just to say, yeah, there were some unusual eruption interval times. Okay, and I'll tell you, and we'll look at those there. So that could be checked as my unusual feature there, okay? Everyone all right with that one? Okay. And then let's go to, I have two different home run distributions. We have a dot plot, or one distribution, two different displays of the home run data. We have a dot plot and then we have a stem and leaf display. So I'm going to go ahead and look at that stem and leaf display there. And when I'm looking at them, again, I like to turn them on their side so that I can really kind of visualize the distribution in terms of how I'm used to looking at them. Okay, and again, this one is going to be the same story. I'm going to say unimodal and fairly symmetric again. So again, context. We'll write out the same list in the same order that we did for the last one. So we have context, we have shape, we have center, we have spread, unusual features, and I guess I didn't put it in the same order, but that's okay. 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 So the distribution of the seasonal home run totals okay, so telling you exactly what that variable represents, this is for Barry Bonds, is, okay, you might get a different perspective on what that distribution looks like if you're looking at the dot plot rather than the stem and leaf display. Some might say that this is slightly skewed to the left. I'm just going to go ahead and go with my fairly unimodal. Again, when you have very few data points, it's kind of hard to really make a decisive decision about what that distribution is, what shape that's actually taking on. But let's just go ahead and say that it's unimodal and fairly symmetric. With a median of 34 home runs and an IQR of 20 home runs. Okay, so the range of the middle 50% of the distribution is 20. Okay, and then I'm just going to say, if I want to talk about range as a verb, I'm going to say these totals, I'm not using it as a single value, these totals generally ranged from, okay, and I'm going to leave out this unusual count of 5, and I'm going to say they generally ranged from 16 to 49. But then I'm going to talk about those 2 unusual seasons where he had 5 home runs and then the other one where he had 73. Okay? With 2 unusual seasons. Of 5 and 73 home runs. Okay, and as I said earlier, if we used our 1.5 IQR rule, this 73 ends up not being an outlier, but it's still very unusual to us, so it's worth pointing out. That's a conservative rule. It doesn't mean that we can't still call it unusual, even though it's not defined an outlier by our conservative rule. Okay? Okay, so putting all of this together, all right, I want you to now be familiar with learning how to create a distribution using the different, for a quantitative variable, using one of the 4 methods that, or all of the 4 methods that we've learned, okay? Figuring out what types of measures to use for your measure of center and spread, and then being able to put it all together in a nice description. So those are the main things that you should be taking away from this chapter, okay? And if you need work on your writing, then bring in some recommended problems, and we can give you some critiques on your writing if you want that. Okay? All right, so let's go ahead and look at another learning catalytics question. Okay. All right, so here is the question. I want you to tell me, given this distribution, these are the number of concerts attended for this class this fall. A nice histogram. And I just want you to tell me which would be the most appropriate measure of spread for that distribution. And we'll just take 15, 20 seconds for this one. Today, and if you do have trouble getting logged back on, don't panic. Please do let me know after class if you do have struggles with that. Let's go ahead and talk about that one. Go ahead and get your answer in. Okay, and it looks like 70% of you chose D, which is IQR. Okay, let's just go through these. Remember that the mean is a measure of center, standard deviation is a measure of spread, median is a measure of center, IQR is a measure of spread, and mode we actually haven't talked about too much. Mode is just the most frequent observation, or you could talk about the modal interval, but that's also considered a measure of center. Okay, so these B and D were really your only options, and then D, since we have a quite skewed distribution with outliers, that would be the most appropriate measure of spread. Okay? All right. So I think that I'm going to leave it at that for the learning catalytics, and let's go ahead and move right into chapter 4 and start talking about understanding and comparing distributions. This is page 43 of your notes. Okay, so the question is, could it have been both the standard deviation and IQR for that last question? So yes, standard deviation is a measure of spread, but we don't want to use it when we have outliers and skewness. And so that was the reason why we just wanted to choose the IQR, because that was a severely skewed right distribution with some quite unusual points. Okay? All right. So now, like I pointed out with those migration data, those migration speeds, now we're going to be able to use these box plots to compare multiple distributions. Okay? And the box plots are really nice for making these multiple comparisons. And you'll see why when we start to get into more and more groups that we're trying to compare across the same variable. But let's just go ahead and jump into an example, and I'll illustrate how we're going to create these box plots, and then just a nice lead into why we even like using these, because they do take away a lot of the information from a distribution. Okay, but there are definite reasons why we would want them. Okay, so we have some interesting historical data. So between June 5th and July 2nd, 1879, we have this scientist, Albert Michelson, and he conducted 5 different experiments to attempt to measure the speed of light. All right, and so the following observations display data from 2 of the experiments. So we're just going to call it Experiment A, Experiment B. And all of these measurements are in kilometers per second. And all of the measurements have also had 299,000 kilometers per second removed from it. So then we just have these leftover values, okay, just to make the calculations easier so we don't have to write these huge numbers every time, okay? And now we know that the actual speed of light is 299,792.458. All right, and so that gives you kind of a reference relating to where these experiments are giving those estimates. Okay. So we have Experiment A, Experiment B, and we have an odd and an even case of data values. All right, and so if you want some more practice with finding those 5-number summaries, I encourage you to go through and do this and check to make sure that my answers match your answers. But I'm just going to go ahead in the interest of time. I think that we've seen this quite a bit now. I'm just going to go ahead and list the 5-number summary for each experiment. Okay, so we have 650, and this is a fine way to display a 5-number summary. Just like that, just making sure that they're in order, right? So that a reader can definitely understand what's going on there. Okay, so those are the 2 5-number summaries. And now we're just going to use that 1.5 IQR rule to check for outliers. Okay, so I still need to keep my data there. I need to have my data in hand when I'm using this rule. Okay, and so I'll just remind you. So we have Experiment A. Ooh. Okay, and then we're going to do Experiment B over here. Just remind you what we need to do. Let's see here. So we'll say the lower fence for Experiment A is going to be, remember, it's Q1 minus 1.5 times the IQR. And in this case, 980 minus 850 is 130. So that's going to give me the IQR. And I get 655 is the lower fence. Okay. So do I have a lower outlier if my lower fence is 655? Yeah, right? If I look back up at my experimental data here, it went 650 and then 740. Okay, so 650 is an outlier, but 740 is not. So I'm going to go ahead and write in that 650 is an outlier. Okay. The 130 is the IQR, and that is the 980 minus 850. Okay, and then we have the upper fence. Again, remember that these fences we don't plot, they're just the outlier boundaries. So the upper fence is going to be Q3, which is 980 plus 1.5 times the IQR, and 5. And I don't even have to look at my data because I see that my max is 1,070. So I know that I don't have an upper outlier. Okay? So we'll say no upper outliers. Is that okay with everyone? Okay. Let's do the same thing for experiment B. The lower fence is going to be 805 minus 1.5 times. Okay, now I have my IQR is 860 minus 805, so that's 55. 1.5 times 55, and I'm left with 722.5. Okay, so I see my minimum is 740, so I have no lower outliers. My upper fence is Q3, so 860 plus 1.5 times that IQR, and that is 942.5. Okay. Do I have an upper outlier? Yeah, right. So 942.5 is less than that maximum of 950. So I better go up and double check that I don't have more than one outlier. Okay, so I have 940 is one value, and then the biggest value there is 950. So it looks like my only outlier for experiment B is that upper outlier of 950. So upper outlier of 950. Okay? So on Wednesday, what we're going to do is we're going to put this information into this table and create side-by-side box plots of these speed of light estimates and then get a nice comparison. Okay?